Hi, our group did a machine learning project on converting handwritten math symbols into latex. My name's Ka.
My name is Biraj.
And my name is Alvin.
And our machine learning algorithm first receives an input, such as this, that contains an image of a mathematical written equation. And our algorithm pieces each component into its own section, then gives its output of what it should be in latex, and we use that to produce our latex equation. Now Biraj will talk about his diagram related to this project.
So this is an overview of the entire project. So as the class said, we take a picture of the equation, then we pre-process the equation using some computer vision techniques. Then we do connected component labeling, which extracts each symbol from the image. At the same time, we recognize where each symbol is within the image. We feed each symbol into this neural net, the convolutional neural net, and we take the classification from the neural net along with the locations that we found earlier to create some latex string that hopefully represents the equation correctly. Now, Alvin is going to talk about a bit of the data processing.
So the source of our training data was from Calvo.com, and what we got was a zip file of about 60,000 images that looked something like this. The major problem with these images are that they are super thin, and it's very hard to convert a real-life image into something this thin. So some pre-processing steps that we did were 1, binarize them, 2, fill in small holes like these, and 3, dilate them to make them thicker. And Biraj is going to talk about more of the pre-processing that we did on the real-life images.
So let's say you had an image such as this. You basically want it to be like this so that you can feed each symbol into the neural net, and this is how we kind of did it. So right here, let's say you have this as your original input image. What this is simply removing a bit of the noise using something called a Gaussian blur. As you can see, there's still a lot of noise from lighting that takes place here, lighting and bad paper quality. So after this Gaussian blur, we did something called a adaptive threshold. What that does is it thresholds this image locally to remove a lot of this noise, as you see right here. Now this is a lot better, but there's still a lot of salt and pepper noise, and to get rid of the salt and pepper noise, we use something called a median blur. Now the median blur will do this. This is really, really good, and in fact this is actually a dilated image as well. We perform dilation. As you can see, the symbols here are super thin, but we dilated them to make them thicker, and we perform connected component labeling to label each individual component, and we get the correct components back. Now Alvin will talk a little bit about the neural net.
The model that we decided to train the data on was a convolutional neural network from TensorFlow, and we based the architecture off the Linnet architecture, which is basically just 2 convolution layers with pooling attached to a fully connected neural network. We trained the neural network about 5 times using different parameters in batch size and epochs, and we found that the parameters specified in this notebook were the best, and that resulted in an accuracy of 99% on the cross-validation set.
So now once we have the classifications done and the location of each symbol, we have to actually make them into latex. So this is that classifications, and as you can see, they all classify correctly, which is really cool. And what we're doing is we're basically taking each image and we're splitting it into groups based on its location, and then taking each classification and trying to output its latex. So this function right here will do all of that for you, and in the end you get this string, and if you render this as latex, you get this. Now Kyle will talk a little bit about a cool web app that we made as well.
Yeah, as you can see, our models were really good, so we went a step further and froze the model to serve it on a separate API. And here's a simple web app that runs on Flask to basically test that API. And from the Jupyter Notebook, you recognize this image, and basically we can click Analyze, and it'll send an asynchronous request to our machine learning model in the server and return to us the output of the machine learning model. And as you can see, it's the same as the Notebook. And it's good for convenience for testing other images, such as this. And so we can try a bunch of different images and get feedback on our model instantly. And now Biraj will talk about the conclusion of our project.
Sure. So one big issue that we have is the fact that handwriting and typewriting is so varied, because everyone writes differently and there's so many different fonts. Now, this is a big problem for OCR, optical character recognition, which this is, and that's why this is still an open problem in the research space. And we obviously fell upon this problem as well. That's why, as you can see here, the latex classification is incorrect here, as well as many other images. In fact, most images, they probably won't work because of just how varied everything is. As you can see, it's close, but it's not perfect. That's our project. Thanks.